Alright, so in this video we'll start discussing Phillip Hall's theorem, but first I'm going to do some lead up to it by going back and talking about Lagrange's theorem. As you might recall, Lagrange's theorem says that if you have H a subgroup of G, then the index of H and G divides the order of G, at least when H and G are finite groups. So we're going to stick with finite groups for now. An obvious corollary to this is that the order of H divides the order of G. And so a question that one often asks is about the converse to Lagrange's theorem, which is given a divisor of the order of G, does there exist a subgroup of that order? And we're in the valley, so let's put the question mark upside down, and now it's proper Spanish instead. And so one example we've seen is that if G is a P group, then the answer is yes. And an example they sometimes cover in an undergraduate course is if G is A4 and D is 6, then the answer is no. And I think earlier in the semester I did another example with G being, I think, was it S5 and D was 40 or something like that. I can't remember off the top of my head, but I did another example where I took a large group and I proved it didn't have a subgroup of a specific size. So actually this should be what you call a non-example because it's where the statement's false. But one thing I neglected to mention was if G is nilpotent, then the answer is also yes. And why is this? Because G is isomorphic to a direct product of its CELO subgroups, and each of them is a P group. And so if you factor D as P1 to the A1, PK to the AK, you know there exists QI, a subgroup of PI, where the size of QI has the appropriate order, PI to the AI. Then Q1 times Q2 times ... times QK is in fact a subgroup of G, of isomorphism, of the appropriate order. So for nilpotent groups, the full converse of Lagrange's theorem is in fact true. Every divisor of the group gives you a subgroup of that order. Of course, as we know, in complete generality, for arbitrary groups, the best converse we have for Lagrange's theorem was CELO's theorem, which had to do with what happens when you factor the order of G as a product of prime powers. Then we know there exists a subgroup of G whose order is that prime power of highest exponent. So the highest exponent k such that p to the k divides g, that is the order of the CELO P subgroup. and that CeLO P subgroup in fact exists. And because it's a P group, as I've mentioned before, that actually implies that for all prime powers dividing the order of G, you can find a subgroup. With that size. Unfortunately, we can't do much more than that, but it turns out for solvable groups, there are two stronger statements you could make along these same lines. And I will state both of them for now in this video, and in the next video we'll focus on proving the first one, which is called Phillip-Hall's theorem. But the other one is related, and since I'm going down this road, I might as well talk about both of them. And so the first one has to do with, well, we already see that there exists P1 with order P1 to the A1. The claim is if G is solvable, then you can also find HI, whose order is the product P2 to the A2 dot 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 PK to the AK. So the intuition here is, remember, when G is nilpotent, then it's isomorphic to its product, direct product of its CeLO subgroups. Remember, that also means, of course, that if you remove any of these factors, that say the direct product of P2 through PK is isomorphic to a subgroup of G, P1 times P3 times PK is isomorphic to a subgroup of G, etc. And so the point is that for G solvable, a similar statement is true. Oh, here I have HI, I should have H1. When G is solvable, you can find a subgroup whose order is the order of G, except for that one prime that you're dividing by. So you get rid of exactly one of these prime powers and you keep the rest. There is a subgroup of that order. They call such an H a CeLO P complement. And the concept behind the terminology, as I mentioned before, is if you have a subgroup of G, the complement of H is a subgroup K, such that H times K is G, and H intersect K is the identity. Not every subgroup has a complement, but it's useful when you do. And so the point is that solvable groups, while more general than nilpotent groups, still manage to maintain this property of nilpotent groups. And as we'll see, actually, Phillip-Hall's theorem is that this is an if and only if. And that's supposed to be the true power of Phillip-Hall's theorem, but this direction of Phillip-Hall's theorem is kind of interesting on its own right. So the theorem is that G is solvable if and only if every non-trivial Hall Pi subgroup let me add in the word non-trivial there. As a complement. So the word non-trivial here is supposed to convey the fact that we are obviously supposed to be assuming that G is finite and that whatever this P you've picked is, it must divide the order of the group. This is one way to state the theorem. The textbook actually writes it out in terms of products of powers, and that makes the statement a little harder to write. But this approach works as well once you've defined the terminology. This theorem is so famous that they actually have terminology as a result. A Hall subgroup is a subgroup with the GCD of its order and its index being exactly 1. Why? Because that's exactly what happens in this case. Its index is exactly a power of a prime, and its order is the product of the other powers. It's worth pointing out, actually, Hall Pi subgroups are also Hall subgroups. And then the groups from this theorem. The other generalization of Cielo's theorem for solvable groups that we won't prove involves a generalization of this. So this is exercise 33 in section 6.1. Although there they actually use the terminology correctly, but here I'm going to try to avoid that. The term they use is called the Hall Pi subgroup, where pi is a set of primes. The terminology gets kind of confusing and takes a little bit of grokking to understand, so rather than go the full Monty there, I will just state what they're really trying to say. Is let G be a group, and suppose you factored it as a product of prime powers. And okay. Let me state it more carefully. Suppose you've got a collection of primes that divide the order of G. And so you've managed to write G as P1 to the A1, PK to the AK, times Q, where none of the primes divide Q. You know that you can do this. This is your set of prime. You've taken some of the prime divisors of G, just any number of them. You're looking at that collection of the prime powers. If G is solvable, then there exists a Hall subgroup H of this particular order, P1 to the A1 up to PK to the AK. So this is stronger than the CELO theorem because you're no longer talking about just powers of one prime, you're talking about products of powers of primes. Just like the CELO theorem, though, you can't pick any arbitrary power. The only powers you can pick are the highest powers such that that prime divides the order of G. Unfortunately. But for solvable groups, this is the strongest converse to Lagrange's theorem we have, which means that there exist solvable groups such that you can find composite divisors of G where the powers are slightly lower than the maximum exponents, such that there does not exist a group of that order. And so the full converse to Lagrange's theorem is false. So for solvable groups, you can go a bit farther than CELO's theorem. Of course, in the next video, we will actually focus on this theorem and trying to prove it. It is worth pointing out that this proof is actually not that hard. It actually follows from this one by using induction, because all you're really doing is factoring Q as a product of primes and then eliminating them one by taking complements. And then remembering that subgroups of solvable groups are solvable.